Today we would like to discuss about lecture number 4. We talk about figure of merit, MOS transistor, and region of operations. So these are the topics that we would like to do in this class. Okay. So before going to that region of operations and the figure of merit, so let us recapitulate what we have seen in the last class. Okay. So let us recap. So in the last and the previous classes, we have derived the IV current equation, IV equation for NMOS transistor. Okay. So what we identified that. So we identified that IDS value is 0 in linear region. Is 0 in cutoff, and IDS value is equal to, for example, beta times of VCS minus of VTH into VDS minus of VDS squared divided by 2 that we have derived previously. So it is actually in the linear mode of operation. Okay, it is for linear mode of operation. The current equation is something like this. IDS can be beta by 2 into VCS minus of VTH whole square. So this is in saturation. Okay. So this is in saturation. Everybody knows about this. Okay. So the current equation for the NMOS transistor is something like this. Okay. These equations are holds good. Okay. Provided VGS value is less than VTH. That's what it has to be. It has to identify. And this is also true when VGS value should be greater than or equal to VTH, and VDS value is equal to VDS value is less than VCS minus of VTH. Okay, and in saturation here also this equation must be holds good. This condition must be holds good, and VDS is greater than or equal onwards, or VDS is equal and greater than, maybe equal avvachu, greater than avvachu. So you can expect that there is a constant current can be observed. Okay, so we are using the long channel approximation. Okay, in that situation we don't find any kind of short channel effects. Okay, now let us apply the same kind of equation for the PMOS transistor. So how do we do for the PMOS then? Because we have to use both NMOS and PMOS in CMOS designs, therefore we should understand some basics related to NMOS also. So sorry, PMOS also. As everybody knows that whenever we are realizing the PMOS transistor, the substrate must be N substrate. Okay. We know that there is a gate oxide. On top of it, we have a polysilicon. The source must be E plus, drain must be E plus. Okay, and our requirement is that what is our requirement? We have to create an inversion channel near the silicon dioxide. Okay, at the surface. That means minority carriers of the electrons, minority carriers of the substrate must be attracted towards the gates under the gate oxide. Okay, so this is possible by applying the since n-type is holes must be attracted towards. That means what is the charge that we have to place on the top of the metal? The negative charge that we have to place, right? Then only the positive charges will be attracted here. I agreed. Electrons will be attracted here. So that means that the gate voltage must be negative. the gate to substrate voltage must be negative. That means that, as we mentioned, that whatever the VTH of the PMOS transistor should be a negative voltage. So as we mentioned that the threshold voltage of a transistor is nothing but a minimum voltage that is required to invert the channel. Okay. So here in the NMOS transistor, electrons has to be attracted. That means positive charge that we have applied. Okay. Therefore, it is meaningful to say that positive charge is applied. Say for positive threshold voltage. So here the negative voltage we need to apply at the gate. Therefore, the carriers are attracted. So that's the reason why it is meaningful to say that there is a positive negative threshold voltage for a PMOS transistor. Therefore, we observe that negative threshold voltage. Okay, please remember. And another point is that the source must be, so we have to send, our requirement is that we have to send the carriers from source to drain. Okay. So whatever the carrier is there, that it has to move from source to drain. What carrier it is moving from source to drain? Hole is moving from source to drain. Therefore, conventional current direction where it should be. So in the hole's direction only. If the carrier is moving this direction, hole is moving this direction, current is also moving in this direction only. Okay, so provided that we have to apply a negative potential here, we have to apply a positive potential at this place, right? We have to apply a positive potential at the source. At the source side, we have to apply a positive potential, and the drain side, we have to apply negative potential at the gate, so that the carriers are able to move from source to drain. Okay, therefore this positive charge is pushing these electrons towards the drain side. Okay, therefore that is what we observe. So therefore the drain is at negative direction, and the source is at also the source is at positive here in this place, and VDS is something like this. Okay. So as we know that the terminal voltages on all these points, therefore, for example, VGS, okay, is negative value that we observe. Okay, it is also a negative value. VDS is also a negative value that we observe generally. Okay, so therefore, what is the current value again? Here also the current is also a negative dash. So if you are considered in this way, VGS is directly, if you consider the negative, VDS is considered in this way negative. IDS is also a negative value if you consider it in this way. But actually original value is where it is coming from, source to drain itself. Source to drain it is moving. Source is at positive and drain is at negative. Okay, so therefore, since IDS is negative, writing the equations in the negative direction is not advisable. So instead, we can write it all these things in a positive direction only with the help of magnitude, absolute values. If you consider the absolute values, then it is equivalent to say that it is NMOS equations only. But provided that all these parameters should be negative. Okay, so what I can write it in this way, I can change. So for the PMOS transistor, whatever IDS we talked about, that's a magnitude value I have to consider, that is equal to 0 under cutoff. Provided, please remember carefully, magnitude of VGS value should be less than magnitude of VTHP. Actually, VGS is negative. VTP is also negative. Instead of negative values, comparison of the negative values is very difficult. Okay, that's the reason why I put it all these are positive by using the absolute values or magnitude values. Clear? Fine. Now, similarly, the magnitude of IDS value is equal to beta times of VGS, magnitude of VGS minus of magnitude of VTHP into magnitude of VDS minus magnitude of VDS whole square divided by 2. So are you agreed? Are you agree with me? This kind of situations. So better I'll use the different colors for the conditions. VGS less than VTHP, something like this. Okay. So this is actually the linear mode of operation. So it is acceptable from VGS value should be greater than magnitude of VTHP, and also this is also applicable for VDS value is less than VCS minus of VTHP. All are magnitudes only. Okay. So therefore, so we need not think about the negative comparison. So we can do it VCS values and VDS values, take the magnitude and compare the things. That's all. As simple as that. So then IDS value is equal to beta by 2 into VCS minus of, I think better I'll write, magnitude of VCS minus magnitude of VTHP whole square. So it is said to be in saturation. This equation governed by the saturation current saturation region, provided VCS value should be less than magnitude of VTHP. Sorry, it should be greater than magnitude of VTHP, and the VDS value, magnitude of VDS value is it is greater than or equal to magnitude of VCS minus of magnitude of VTHP. I hope you understand this concept. Okay, whatever I have done here. So for the NMOS transistor, positive current only be observed from drain to source. If you want, but it is not possible for the PMOS transistor to write IDS because the current is flowing from source to drain, not from drain to source. So therefore, if I write the IDS directly, I have to mention the negative current values. That means I need to put all this negative so that I can remove the absolute values. But it's not advisable one. So better you have to consider the IDS current only. Okay, that is a negative current only. Okay, but you use the magnitude value so that the readability will be increases. Nothing more than that. Fine. So this is what today we have introduced another one. The last class we have seen another point. Okay, so we have derived the transconductance parameter. Transconductance parameter. So this is called GM. So why we have calculated for the GM? So why we have calculated for GM? So in order to identify the fastness of a transistor, in order to identify the fastness of a transistor, we have to know the GM value. For a fast transistor, GM should be high. Okay, if you say that, if you want to make fast transistor, the transistor should have high GM. So GM value must be very high, then only we can say that the transistor is the fastest transistor. Okay, so then what is the dependency of this transistor that we have seen? The GM dependency is, in order to increase the GM, we say that it is in the terminal point of view, VCS minus of VTH we have mentioned. Okay, it is also proportional to, W by L ratio. Okay, or simply W. But here also we mentioned that it is inversely proportional to that of. Okay, W by L ratio only is depending upon, but we don't bother about W. So we don't want to interest on W, because if you increase the W value, the gate capacitance will increases. It's not a solution. So only the solution is that decrease the length of the transistor. So these are the two ways that we can increase the GM value. That's what we have derived in the last class. Okay, now. So now today let us consider a very important one is figure of merit of the MOS transistor. Figure of merit. MOSFET. What do you mean by this one? So for the switching speed of a transistor, is not only depending upon the GM, it's also depending upon what is the gate to channel capacitance. Okay, so therefore the switching speed of a MOS transistor is not only depending upon GM. So far we thought that the GM only the parameter which we can increase the fastness of the device. Okay, so the switching speed, that means how fastly the transistor will take the input and convert it into the current. So as soon as how faster it will switch from one state to another state, on to off or off to on state. Okay, in order to identify this one, we should know the frequency response of a transistor. Okay, so that means that if you want to identify the fastness or the switching speed of a transistor, we should know the frequency response of a transistor. That frequency response is measured by omega naught. So that is measured by a parameter called omega naught. So this parameter is responsible to indicate the switching speed of a transistor. Okay, so how do we calculate the switching speed of a transistor? It's just a frequency response of a transistor. Okay, so anyway, so the switching speed of a transistor is measured by omega naught, which is decided by GM by CG of a transistor. So therefore, the omega naught is normally we can call it as figure of merit of a transistor. So the figure of merit parameter of a transistor means omega naught we have to calculate. So therefore, it indicates the switching speed of a transistor. Okay. So therefore, what I can say here now. So the frequency response, if I can write a small statement here, the frequency response of MOSFET is indicated by omega naught, which decides the switching speed of a transistor, Okay, as simple as that. Now let us identify the dependency of omega naught on these parameters. Let us look at that. So as we know that omega naught, what is the GM? As everybody knows that. So in a formal way, I'm writing in all the parameters for a NMOS transistors, mu n into Cox into W by L into VGS minus of VTH, considered for NMOS transistor, divided by, what is the CG? Cox into W into L, right? That's what we have calculated previously. That's how we have calculated previously. Gate to channel capacitance over the entire area of the gate to channel. Okay, so in that situation, we can remove Cox and Cox, W and W. Okay, so therefore, what we can observe that omega naught is mu n into VGS minus of VTH divided by L square. So this is how we have to identify the switching speed of a MOS transistor. If we want to increase the switching speed of a MOS transistor, okay, so we have to play with these kind of parameters. Okay, so therefore, what we can understand about it, for example, let us consider some observations. The first observation is that everybody knows this one. So omega naught is proportional to that of VGS minus of VTH. So how much fast the transistor is switching from one state to another state is decided by how much sufficient voltage that we are applying at the gate. How much sufficient voltage that we are applying at the gate. That's what we have to remember. Okay. Of course, we know very well about it. The second point is that omega naught, if you want to increase, so L square also we have to use. That is as small as if you are decreasing the length of the transistor by a small amount, okay, the omega naught will increases drastically because the square dependency is there. Okay, if the length of the transistor reduces by a small amount, the omega naught will decreases by omega naught will increases by a large amount. That's what we can observe. Now, very interestingly, we write the third point that is called omega naught is proportional to that of mobility of the electron. So far, we have seen that the mobility of the electron is constant. In generally, we have assumed that the mobility of the electron is constant. But when you come to the point of discussion for the calculation of the exact values of the exact current values, mobility is not constant in a surface as well as the transistor. That means in the transistor. So let us see what are the dependency of the mobility on the transistor. Okay, let us see. The mobility of the carrier in a transistor. Okay, point number one. So the mobility of the electron or maybe a hole, whatever it may be. Okay, so that's depending upon the cutting of the wafer. It's depending upon the cutting of the wafer. That means that the wafer is cut into different orientations, whether it is 100 orientation or it may be 11 orientation. So the cutting of the wafer will decide the mobility of the carrier. That's what we can observe. So what is observation here now? It depends on, I can write it here. It depends on the orientation of the crystal. I can simply write the orientation, cutting orientation. Orientation of
Hello,
crystal.
sir. Hello.
So there are the two possibilities are there. 100 orientation is there. And normally these are the two orientations people will try to cut the wafer into these orientations only. 100 orientation or maybe 111 orientation. Okay. So therefore, the mobility of the carrier at 100 surface is larger than 111 orientation. For what we can say that? So the mobility of the maybe electron at hole, it doesn't matter. The mobility of 100 oriented carrier is greater than mobility of the carrier at 11 oriented crystal. I can simply write it this way. So that's what we have to remember. So that means the mobility of the carrier is not constant. Mobility of the carrier is depending upon the orientation of the crystal. How we are cutting the wafer actually. The second point is the carrier, where the carrier is available in the transistor, whether the carrier is available at the bulk or the carrier is available at the channel or maybe a surface. Okay, so therefore it depends on, next one is it depends on the availability of the carrier in a transistor. Okay, in a transistor. So as I mentioned that I can simply write in this. So for example, you consider a transistor here. We have a source, we have a drain, n plus, Okay, P substrate we considered P substrate. Okay, so of course we know that there is a we have a oxide on top of it, we have a polysilicon. So observe that. So the carrier can be observed here. Okay, so that means the carrier can be observed at the channel. Let us consider here is the channel is available. Sorry, I'm extremely sorry. The carrier is available in the channel. Okay, and the carrier is also available in the bulk. For example, electron. The electron that is available in the bulk and the electron available in the channel have got different mobilities. Have got different mobilities. For example, the mobility generally we can say that surface mobility of the electron or maybe whatever the carrier it is, which is greater than the mobility at the bulk. Mobility of the carrier at the bulk. That's what we have to understand. Generally, if you consider, for example, you consider the surface mobility of the electron. For example, we considered an electron. Okay, this is equal to 650 centimeter square per volt second. That's what we observe. The same electron, if it is there in the bulk, for example, bulk electron, it will be 1250 centimeter square per volt second. So that is the difference. Okay, so the mobility at the same time, the we can say in the different fashion also, but it is a, whether it is the electron, whether it is hole, it doesn't matter because everybody knows that the carrier mobility. So the carrier mobility will be, extremely sorry, just a second. His net is disconnected. Yeah. So what we observe that when we consider about, for example, the hole, for example, generally when compared to the hole and electron mobility, for example, of course, the third point, let us consider this one, everybody knows that the mobility of the electron and mobility of the hole. Okay, whether it is in the surface or whether it's the bulk. Okay, whether it is in for example, whether it is in I can say that different orientation, it doesn't matter. All the time, this will be more than that of the 2.5 to 3 times it will be. The mobility of the electron is 3 times than that of mobility of the holes. Generally, it is holes 2.5 to 3 times. It will be happening this one. Whether it is a bulk, whether it is a surface, right? So this is what we can observe about the mobility of the electron on the speed of the device. Okay, so not only the VGS minus VDS, not only the length, it is also depending upon the what type of material or what kind of environment that we have created for the carrier. Okay, so that's it. So according to that, according to those kind of things, we have to play with that. Okay, fine. Now let us see the region of operations of a transistor. Okay, so there some problems are coming on this area. So let us discuss that one. Region of operations of MOS transistor. How do we identify MOS transistor region of operation for the different values of gate voltage, source voltage, and and at gate also. Okay. So for that one, there is small hint is required here. Okay. For example, if we consider a MOS transistor, something like this. Here is the gate. Here is the drain. Here is the source. The current is flowing from drain to source. And this is the symbol is used for NMOS transistor, enhancement NMOS transistor. Okay. Similarly, if you consider a PMOS transistor, something like this, for a PMOS transistor, we use in this way. This is the source, this is the drain, this is the gate. Okay. So what we observe that generally, please remember that source is, sorry, the drain is, when compared to the drain and source, VD is at positive potential and VS is at negative potential, or maybe ground also, doesn't matter. So here, most of the cases, VS is actually a positive voltage that we apply, VD at the negative. Okay, we cannot say like that. Okay, don't worry about it, but a general discussion only. But anyway, the potential at the source is higher in case of NMOS transistor. The potential at the potential at the source for the PMOS transistor is also high. So sorry, I'm sorry. So the potential at this gate, potential at the drain is higher than that of the source. The potential for the source is higher than that of the drain in case of PMOS transistor. Okay, yeah, I will write here. Please note down this point. Okay, the potential at drain is larger or in general large than source. It is in case of NMOS. Okay, so here, but whereas in PMOS is different. Okay, the potential at the source, very important, source is larger than drain. So this point will be very clear later point of time. Please remember. Okay, this is in case of PMOS. Okay, so this is an NMOS transistor. This is a PMOS. Please remember that unless otherwise, if I'm not mentioning it is a depletion mode, every transistor is enhancement type mode transistor only in terms of the power consumption point of view. Okay, fine. Now let us see. This is the usual practice that we do, or this is also people sometimes will use. Okay, for NMOS transistor, I don't want to show the current equation, current directions. This is for NMOS. Bubble we have to use sometimes for PMOS. Okay, so this is for NMOS. This is for PMOS. Both are applicable. Okay. So, for example, let us write here. What is the usual procedure? Conventional approach to find the state of the transistor, and some shortcuts also we will get. So if any transistor, in case of NMOS, everybody knows that in case of NMOS, if VGS value is equal to, if VGS value is less than VTH of a transistor, the MOSFET is said to be off. Okay. If VGS value is greater than or equal to VTH, then the MOSFET is said to be on. Here 2 points are there. One is VGS value, sorry. One is VDS value is greater than, less than, I'll write first, less than VGS minus of VTH. Okay, it is called linear mode of linear region of operation. When VDS is greater than or equal to VGS minus of VTH. This is in saturation, right? Saturation. So the same kind of thing is applicable for the PMOS also, provided only we have to use absolute values. Okay, so I'll write here all these things. Again, I don't want to write. Okay, so I'll put it here. So just only I have to consider the absolute values. That's all. Where you find this one? Okay. Now let us apply these kind of things here. So the conventional approach is this one. Shortcut also I'll do. Okay, we will go for the shortcuts also. What we do is that, suppose, let us consider an NMOS. If NMOS is, sorry, let's consider here. If the gate potential is equal to the drain potential, the transistor is set to be in saturation. Just observe the potential at the gate and observe the potential at the drain. If the gate potential is equal to greater than the drain potential, in this situation, it is said to be in linear, provided that these kind of things are applicable. First, you have to identify that VGS value should be greater than VTH. There is no doubt at all. Okay. And the source must be connected to ground. Source must be connected to ground. If source to ground connect చేసి VGS may greater than threshold voltage కనుకుంటే, then we have to play with gate and drain. That's all. Same thing is applicable for the PMOS also, provide that magnitudes of the VC, magnitude of drain that we have to consider. Okay, so let us apply these kind of things in our one example. So we take this textbook. Let us write some examples. Just a second. Let us consider these some examples. Okay, snapshot, snippet 2. Okay. And then paste it. Okay, so these are the some examples I have taken. Okay, so let us understand whether the transistors are said to be in linear or saturation. Okay, or it is off. Okay. So to assume that, VTH-N, for example, is 0.4 volts. VTH-P is equal to minus 0.4 volts, for example. Okay. So what is the region of operation of this particular first transistor? Okay, you find out whether it is NMOS transistor or a PMOS transistor. Roll number 5, Nikesh. Somebody, or maybe he's named the person, somebody in the class. So is it a M1 is NMOS transistor or PMOS transistor?
NMOS, sir. Hello.
So current is coming out of this terminal. Current is coming out of this terminal. So as I mentioned in this way, current is coming out of the terminal. Please, or maybe you can write it on the chat box also. Yeah, exactly. It is a NMOS transistor. Okay, so therefore it is an NMOS transistor. So now we have we have a gate that is applied, that is available at the ground. Ground is nothing but a 0 only. 0 we have applied. The drain is also at 0, but source is at 1 volt. Something like this. The source is available at 1 volt. This is at 0. This is at 0. Can you say what is the mode of operation of this transistor, whether it is off or on? What we can say? This is 0 volt. Ground means 0 volt. This is also 0 volt. This is 1 volt. Somebody can respond in chat box. It's off. As simple as that. If the gate voltage immediately, first of all, we have to consider that whether VCS value is greater than threshold voltage or not, we need to identify. Greater than or equal, or less than VTH. This is the first step that we have to do it. Okay, so we have a gate to source potential. What is the gate to source potential? 0 minus 1 volt. Okay, which is must be compared with 0.4 volts, since it is a NMOS transistor. So what is the relationship? -1 is always less than 0.4. There is no doubt at all. So that means once the transistor is in VGS minus VTH, therefore the transistor is said to be in off mode. It is in cutoff. I can say that. It is in cutoff. Right. Similarly, what about this condition? The second one, B. Let us consider B here. So this is provided the source is at 0. The gate is at 0. But the drain is at 1 volt potential that we applied. The drop between this terminal to the ground is 1 volt. The voltage source we have applied is 1. So as we know that, first gate to source we have to compare. Gate is at the VGS that we need to consider. VGS. What is the VGS? VG minus of VS. VC at 0. Source is at 0. 0 is at the right hand side. So left hand side. What is the right hand side? Threshold voltage. So is it greater than or less than? Always less than. Therefore, the transistor is set to be in cutoff only. It is also off. What about this one now? See. So the gate is at, so usual practice, I will write it in this way for simplicity. The gate is at 1 volt. The source is at 0.2 volts. The drain is at, the drain is at 0.2 volts. The gate is at 1 volt. So therefore, what we have to do then? Again, we need to compare with VGS minus VTH. What is the VGS value with VTH relationship? VGS is equal to 1 volt minus of 0.2 volts. It is nothing but VGS, the potential difference between the gate and the source. This is actually 0.4 volts. So what is the value here? 0.8. What is the relationship between 0.8 and 0.4? It is greater than. So the transistor is on. If the transistor is on, we need to say whether it is in linear or saturation. So I cannot apply here. You observe that I cannot apply the shortcut here because the source is at some potential is observed. Source is all the source has some potential. That's the reason I don't have any choice. I have to go for the conventional method. Okay. Now, once it is on, then we need to decide the relationship between VDS and the VGS minus of VTH. So VGS minus of VTH, what is the value? This is a 0.8 minus of 0.4. This is 0.4, right? So VGS ఎంత అవుతుంది 0.8, VTH ఎంత ఉంది 0.4. What is the VDS value? Drain to source. Drain is at 0.2. Source is at 0.2. What is this? That is 0.4. What is the relationship between the left hand side and right hand side? It is less than, sorry. Yeah, it is less than. So when VDS is less than VGS minus of VTH, that means here the relationship is less than relationship. That's what it holds for. Okay. So therefore it's less than means what it is, what we can say that it is in linear on transistor, that it is in linear. So this kind of theory is required when we are going further and further in the circuit designing. Okay, so please remember that. So similarly, can you do it for the D? Someone in the class? For the D, what is the reason of operation for the D? Someone from the class, please respond through the chat box. It is in saturation. Please verify once. See, here is what happening. First we have to check for VGS, right? And we have to compare with VTH. What is the threshold voltage of NMOS transistor? 0.4 I have given already. What is the potential difference between the gate and source? Gate is available at 1 volt, source is at 0.7. Therefore, what is the relationship between these two? It's a 0.3, right? 0.3 is greater than threshold voltage? No, it is less than 0.4. So therefore, the transistor is said to be in cutoff. So the transistor is off transistor. Please remember, understand the concept clearly. Yeah, rule number 7, that's right. Say off transistor. So the first thing is that whenever you want to identify the region of operation of a MOS transistor, first and foremost important thing is that we have to check VGS value with VTH. Once that is satisfied, greater than the relationship between the VGS and VTH is a greater relationship. That means VGS is more than that of the threshold voltage. Then you think about whether it is a linear or saturation. Otherwise, the transistor is set to be in off mode only. Okay. So therefore, please identify. I'm going to give you the homework for the tomorrow's class. So everyone from the class have to solve this problem and come to the class. Once this is completed, then only we will move forward. If not, I cannot move forward. Okay. So this is the homework that I'm giving. So find the region of operation of the transistors. Find the region of operation of the transistors for all these things. Okay. So it's a very easy. The concepts are cleared beforehand. You please identify that the region of operation of all these transistors. Okay. So put your concentration and do it. It's a very easy. Okay. So if you have tomorrow, I'll ask the questions on top of it. Okay, on this particular things only. You please come forward with the proper explanation. Those who have give the right explanation, what the reason of operation of these transistors, I will consider it for them for the quiz exam next. Sessional quiz will be considered based on the one-to-one interaction in the next class. Okay, we stop it here today. We will see the remaining things in the next class. If you have any doubt, please send it your queries in a Moodle's platform only. Thank you, Anand.